This is the presentation on 226, part 1, and then I'll do part 2 here, what I did on 227. But on 226, or 126, excuse me, January 26th. And this is the preview activity of which you're supposed to be doing the preview activity, so I'm helping you with this one. And they're telling us that this is the derivative of f, and so they want us to graph f. Now, normally we would call this f, and we'd call this capital F for the antiderivative. But if this is the derivative, then this is the antiderivative. So when they're not using that notation, they're doing f prime and f. So we're doing the antiderivative. Now, the antiderivative, we don't know where to start. The area under the curve, which we've been calculating, just tells us how much the antiderivative changes. But they do tell us where to start on this one. They give us an initial condition that we should start f, the antiderivative, on 0 and at the height of 1. At 0, it's a height of 1. So I got to be here. Now, prior to that, over here, this has a slope of, this is 0 all the way through here. There's no area. So the function wasn't changing any over that stretch. Then, since this is 1 by 1, the square is worth 1, and so this triangle is worth 1/2, which means the graph has to go up a half a unit from 1, so it's at 1.5. So I could say f of 1 is 1.5. Now, to get from there to there, I have to think about what this is. This is a line. It's actually y equal x. And the antiderivative of y equals x is, this is to the 1 power, so I raise it to 2, so it becomes 1/2 x squared, because I have to divide by the new power. So that's a parabola. And more specifically, it's a positive parabola, and so it's curving up. So it's concaved up. So I need to go from here to there in a parabolic curve. Okay? Now, this area is 1/4. It's a half wide, 1 tall, and so a half times 1 is a half, and then half of that, for it being a triangle, is a quarter. So I need to go up 1 more quarter by 1.5. So f of 1.5 is 1.75, 1 3/4. At 1.5, it's up another quarter, at 1 3/4. And this has a negative slope. It is linear, so it's an upside down or concave down parabola. And its slope is 0 right there, so it has to have a slope of 0 at 1.5. And then we lose a quarter here. So by f of 1, we're back at 1.5, because I have a negative 1/4 to cancel the positive 1/4. And I'm still got a negative slope, so I'm curved down. Parabolic curve down. And I continue parabolic curve down. In this next unit, I have 1 square, which is worth 1, and I have half of 2 squares, which is 1. So I have -1 and -1, which is -2. So f of 2 was 1.5. F of 3 now is going to be 2 less than f of 2, so that'll be negative a half. If I go from 1.5. So I have to go to negative 1/2 at 3. So, and I'm still continuing with my parabola down. So I'm trying to make this look like the continuation of this parabola. Okay? Now, what do I do? Well, in the next 1 unit, which goes from 3 to 0, so 1 by 3 is 3 half, because it's a triangle, so it's minus 1.5. So from a half, I've got to go down 1.5 more, so I'm going to be at minus 2. So f of 4 is negative 2. But this is a positive slope, so I have to have a concaved up parabola, and the slope is 0 here, so this has to be a vertex of a parabola concaved up. And then from here to here, I have, again, a triangle that's 3 high, 1 wide, and a triangle, so it's half of that. So 3 times 1 is 3, half is 1.5. So I got to go up 1.5 from minus 2, so I'm at negative a half. I'm still doing the same concaved up parabola because it's the same line. Now it changes to a different line here, so I got to do a concave down parabola, but it still goes up because the area is positive, 1.5 from negative a half, so that'll take me to plus 1 concave, and this should look like this shape, only reflected upside down because it's the same slope, but the same slope as this, only negative, so it's got the same curvature down as this has up. And it's 1.5, 1.5. And then this graph goes along 0 with no area, so this stays at that height. So this is the antiderivative graph of this under the condition it starts at 0. So if I were to answer the questions, on what intervals is f increasing? Well, it's increasing in here from 0 to 0.5, 0 to 1.5. Well, you can see that area is positive, and that's what's making this increase. This area is negative, and that starts at 1.5 and goes to 3. And during that whole time where the area is negative, this function decreases. And now when the area is positive, it increases again. So we have increasing from 0 to 1.5 interval, and then from 1.5 to 4, it's decreasing. 1.5, 4. And then we got positive area, so it's increasing from 4 to 6. And I'm using parentheses instead of brackets because at 4, it's neither increasing or decreasing. At 6, it's neither increasing or decreasing. So I don't want to do a square brackets on these intervals. I want to use rounded brackets, parentheses, meaning don't include the ends on it. Increasing, decreasing, increasing. On what intervals is it concaved up? Well, it's concaved up here when this slope is positive. Concave down from 1 to 3 when the slope is negative. When the slope is positive, it's concaved up. And when its slope is negative, it's concave down. So concaved up from 0 to 1. Again, it's not concaved at the end, right here at that inflection point. Then it's concave down from 1, 2, 3, and then from 3 to 5, concave up, and 5 to 6, concave down. So those are the concavities. Is there a relative maximum or minimum? Well, there's a maximum here, and what tells me that is this derivative is 0. Now it's 0 here, but it kept going flat. So this is neither a minimum nor a maximum, because it looks like it could be a minimum on this side, because this is lower than everything next to it. But on this side, it's the same height, so that's no longer a minimum. That's a max because that's higher than its neighbors. Here is a minimum because it's lower than its neighbors. Here looks like it's going to be max, but since it goes straight, it is not a max. Okay? And it says point, so let's label them. This point is 1.5, and the height is 1.75, and that's a relative max. And here we have 4, -2, and that's a relative min. And that's the only ones on it. Now, what are they talking about here? Well, they're trying to say that what you should be seeing is that the difference between F1 and F0, the change in the height here, is the area under this curve, which was 1/2. And that's what we did. We made it be 1/2. It says, what's the exact value of 1? And we got 1.5. Then it says, figure out 2, 3, 4, 5, and 6. We did those. And it says, based on all those responses that we got from these, make this graph. Well, we made this graph. And then we responded. So that's the first part of what we did. That's activity 5.1.1. Now, looking at this, what's happened here? Well, this is the fundamental theorem of calculus. The area under the curve is just the antiderivative at the end, subtract the antiderivative at the beginning. But a more interesting interpretation of this is this thing, where we add f of a to both sides. So now it says, whatever the height of the antiderivative is at the beginning, if you add the area of its derivative from the beginning to someplace later, that will tell you the height at the end, at that later spot, B. So beginning plus the area will get you to the height at the end. And that's what we were doing in this. Okay? And I think I may have had that too high. I hope you can see what I did. Okay. Now, 5.2. Let's do this whole process again. So we have an area of 1/2. This is a quarter of a circle radius 1. A circle of radius 1 has an area pi, so this is pi over 4. This is minus 1/2. Here is minus 1. This is minus 1/2. This is pi over 4. And this is pi over 4. Now, on this one, it says this is f of x. And they use the capital notation for the antiderivative. And it says when you're at 0 in the x, be at a height minus 1. So if that's minus 1, that's where we're supposed to start. Now, before we go through this one, let's find out where we're supposed to be at the end right away. Well, let's see. That would be 1/2 plus pi over 4 minus 1/2, those would cancel, minus 1 minus 1 1/2, plus pi over 4 plus pi over 4. So we're actually adding 3 pi over 4. And we're taking away 1 1/2 because those two halves cancel. So we're taking away 1.5. And this would be our overall change. So if I pull out a calculator and figure out what that is, we'll be able to check and make sure we're ending at the right place. So minus 1.5 plus 3 pi divided by 4 is 0.86-ish. So I should be 0.86 higher than where I start. And if this is at 1, 2, 3, 4, 5, 6, 7, 0.86 higher would be right about there. That's where I should end. And the in-between places, I should be a half higher, because that's positive area. So I'd be here. Then pi over 4 is about 3/4, because pi is a little over 3 over 4. So it's a little more than 3/4, which makes me a little higher than 1/4 at 2. And then at 3, I got to go down a half from a little over 1/4, so a little less than minus 1, or a little bit more than minus 1/4 at 3. Then I got to go down one more, which we make it down here, moving down half 1 by the time I get to 4. Then up a half, no, down another half, so that takes me down to, if that's like 1/4, then this would be 3/4. Then add 1/4. So 1/4 would, no, 3/4, so that's, there's a half and 1/4 would take me back to about there, and then another 3/4 would take me close to there. Okay, so that's kind of the pattern, but what's the shape of the curvature? Well, a straight line is a parabola. Positive slope means it's concaved up. This is close to a straight line. It's not quite. It's a little more area than a straight line. Well, a straight line would be a parabola here, but it has more area, so it'll gain faster here and less fast at the end. So it will be a little bit steeper than a parabola and then flatten out. And then it's a parabola, but concave down. Oh, and this has negative slope. That's why this is concave down. And then this is negative slope, so it's concave down. We got to get to there parabolically, if that's an adverb. And then we got to go down 1. This is a straight line, but it's constant, 0 slope, which means this is a straight line here. Constant slope of -1. And then we have a positive slope, so it's concaved up. Straight line, so it's a parabola. And then this has pretty steep slope, so it's going to gain pretty quickly, and it's positive slope, so it's concaved up, but not much, and then it's concave down. But the centers of this, if it was a straight line, it would be a parabola, but this has got more area, so it will pull it up a little bit faster and pulls this straight line up a little bit faster there. So that's what it would look like. What intervals is f increasing? When it's positive slope, 0 to 2, and from 5 to 7. What intervals is it decreasing? When the slope is negative, and that would be from 2 to 5. What intervals is it concaved up? Positive slope, concaved up, 0 to 1. Positive slope, concaved up, and positive slope here, so from 4 to 6. 4 to 6, positive slope, concaved up. Negative slope, concave down. Oh, and yeah, 4 to 6. No slope, no curvature. At what point does f have a relative minimum? At 5, where this is 0, minimum. Maximum at 2, where this is 0. And it says figure out the exact values for those, and I showed you how to kind of do that already. So that's most of what I did on the 25th. So now let's talk about what I did, or I mean on the 26th. So now what did I do on the 27th? Well, I did a couple things on the 27th. First of all, I gave some practice antiderivatives. I will do those just for those of you who are reviewing for the test and had trouble with antiderivatives. So I'll do those in a little bit here, if I can remember. This was problem number, or the preview activity, which we just did. You notice it's the same shape here. And notice that they got, this graph that we got starting at 1 is this one right here. Now, what they're saying is, though, is that we were told to start at 1. If we were told to start at 3, it would be this graph. If we were told to start at -1, it would be this graph. See, we were told to start 0 at the function at 0 to be -1 or +1, so that's why we started there. Now, it could be other places, and it could be at 2, or it could be any place. But they want to try to talk about what's going on here. And I tried to talk about this just a moment ago, but let's talk about it again here. So it's saying we can find out how high this function is at 1. At 1, is it here, 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 by looking at how high it was at 0, which we had it being 1. They told us to do 1 for the original, but they could have said 3 or -1, plus the area under the curve, and that area under the curve was 1/2. So 1/2 plus 1 will give you the height at 1, 1.5. This is exactly what we did. Okay? But looking at this, they want you to understand this. So I'm going to move it up here so you can see it. If g and h are both antiderivatives of f, g is an antiderivative of this, h is an antiderivative of this, f is an antiderivative of this. These are all antiderivatives of this. They just start at different heights. Then it should not surprise you then that g minus h will be a constant. That the difference in these heights of these g and h will always be the same amount. If f and h would be the same amount. Or f and g, the difference will be the same amount all the way through. No matter where we go, the height difference between g and f is always the same. 2 units. 2 units. 2 units. 2 units. And the difference here is 2 units because they started 2 units lower. And the difference between g and h is always 4 units. Okay? And they go through a proof of that. You can look at that, but that's what it does. Then in class, we said, now let's try this one. So, the original, let's do A here. I'll do it up here. It says the original function, the derivative, because they find the antiderivative, the derivative is absolute value of x minus 1. And hopefully from your pre-calc days, you can know that this is the absolute value is a v, drop down 1, so it would look like this. Going through 1, minus 1 on the y, and minus 1 on the x. Because this is the absolute value, lower 1. So it looks like this. They say draw the antiderivative from minus 2 to 2. Okay, so here's the antiderivative. From minus 2 to 2. Well, we could start any place, unless they give us an initial condition. Oh, when they do, they say at minus 1, we have to be at 0. Okay. Okay, so, and we're supposed to go from minus 2 to 2. So if we go to minus 2, and between minus 2 and minus 1, there's an area that's a half a square, so it's 1/2. The curve has to go up a half, and it ends at 0, so it must start at minus 1/2. This is a negative line, so it's concave down and goes from minus 1/2 to 0. And then it loses a half. It's still a negative slope, so it's concave down and loses a half. So basically we have the nose of a parabola. And then now it loses another half, so we're down at minus 1. This is a positive slope, so it's a concaved up parabola. And then here it gains a half, not lose a half, but gain a half, so we're back to minus a half. It's still a positive slope, so it's a concaved up parabola. So this is representative antiderivative of a parabola that would have been something like this. So we have an upside down parabola, nose, then merging into a right side up parabola. But we're only doing from minus 2 to 2, so we have this squiggle thing. There's the antiderivative. B says, what if we have h of x equals sine of x? So, and we're going to go on the interval 0 to 4 pi. So, pi, 2 pi, 3 pi, 4 pi, and if I make that 1, the sine of x would start at 0, go up to 1 at pi over 2, back to 0 at pi, down to minus 1 at 3 pi over 2, and back to 0 by 2 pi, and up to 1 at 5 pi over 2, and back to 0 at 3 pi, down to minus pi at 7 pi over 2, minus 1 at 7 pi over 2, and back to 0. That's what y equals sine of x looks like. Okay. Now, what's the antiderivative look like? And we're supposed to start, the antiderivative for 0 is 1. So we're going to start at 1. All right, so we need to know what the area is here between 0 and pi over 2. Well, I'm going to tell you it's 1. Then I'll show you why it's 1 in just a sec. But it's 1. So from 0 to, if this is pi over 2, it goes up 1, which would take us to about there. So we go from 1 to there. And this is positive slope, so it's concaved up. It's 0 here, so this should have a 0 slope here and then concaved up to 2. By pi, it's negative slope, so it's concave down. It's still 1 more higher, so it makes it all the way up to 3. And this has 0 slope, so this has got to be flat and coming down, concave down. And that's 3 high. And then by 3 pi over 2 and 2 pi, we lose 1 and then 1. The first one is a negative slope, so it's still concave down, comes back down 1. And then it comes down another 1, but now it's concaved up and gets back to a 0 slope. So it'll go back down to a height of 1 with a 0 slope at the end. And hopefully you're starting to recognize this, and then it's going to do the same thing again as it did here. Go up like this, and by 3 pi over 2, 3 pi, excuse me, and then it's going to come back down to 1 at 4 pi, because we have minus 1 and minus 1. And you should recognize this as an upside down cosine curve, which is the antiderivative of sine. But this cosine curve is not down here. It's moved up from here up 1, 2. And that's what h of x equals. Negative cosine x plus 2. You can also see that the center line is at 2, where the normal center line is at 0. So it's been moved up 2. Okay, now we got one more to do here. And then a couple of quick things. This one, piecewise defined function. All right, and we're doing on the interval from minus 1 to 3. Minus 1, 1, 2, 3. And we're x squared from 0 to 1. Well, x squared goes through 1, 0, 1 like that. But we're only supposed to do it from 0 to 1, not including 0 and not including 1. So not including there and not there, but a parabolic shape like that. This is P. We're not doing the antiderivative, we're just graphing that. This is a parabola, upside down, move 2 to the right. 2 to the right, upside down parabola. So that would go something like that, down by 1, so something like this and like that. But we're only supposed to do it from 1 to 2, not including 1 and not including 2. Not including the 1, where it's at 1, which is at minus 1, and not at 2, so that's open circle there. So it's just this piece. So we have this piece from that, this piece from that and that. Then it says everywhere else make it 0. And we're supposed to go from -1, including -1, so it would be a solid dot, and it stays 0 to get here, which means that'll fill that in, so it's continuous right through that. But then it's not defined at 1 either place, and so it's an otherwise, make it 0, so we've got to go 0. And then it's not defined at 2 and up to 3, so that's all got to be 0, so it's 0 there, and it fills in that hole there, so it's continuous here. This is what P looks like. Now let's find the capital P, the antiderivative, and we're supposed to go from -1 to 3, and P of 0 is 1, which they're going to call our initial condition. It's not at the beginning of the graph, but at 0 it's supposed to be 1. So before that, there's no area, so all the way to -1, it doesn't change in height. And it's solid dot because we're including the -1. Then it increases. If this was a straight line, this would be a half, but this is going to be less than the half that we're going to gain by the time we get to 1. So there's a half, and it's less than that, so it's there. It's curved up, so it's positive slope. So it's good. This is going to be concaved up. This is parabolic because it was a quadratic. And the antiderivative of a quadratic is a cubic, the third power. So this is going to be a cubic, which looks similar to a parabola. It's just a little bit flatter for longer, but it's basically that. And then we got this area, which is negative, and it's positive slope, so it still has to be curved up, but losing height. Well, the only way to do that and get back to the 1 is to make a cusp here and curve it up and get back to 1. And then it's no area, so it just stays flat for the rest of the way to 3. So we get a cusp at 1. That's 1.5, not quite 1.5 high, 1 and less than 1.5. Okay? And that's what that would look like. And that's the kind of stuff you're supposed to be able to do. Now, the last thing I want you to see is this. And if you go to the link in the text to this, you'll get a model where you can grab this, which is a red dot, and you can move it along this curve. And as you move it, it shows more and more area. And shows gaining a lot of area right at the beginning. So the antiderivative grows very fast at the beginning, but it grows less quickly until it gets to a max right there, relative max. Then it's got negative area, so it starts losing, and it goes down, and then it hits 0, which makes it a min, a relative min right there. Then it starts adding area again. And this looks like an upside-down parabola, so this is a big cubic. Okay? So just play with moving that along and see how this dot moves in accordance with this, where the amount of area here is the height of this graph. That's what they wanted you to see on that, and that's what I want you to see on that. Okay, and that strengthens the idea of this. Wherever you start at, they're starting at 0. Added to the area under the curve makes the other curve. It tells you what the the final height is for the area added up to that point. Okay. All right. I did a couple antiderivative problems in class, and they were a little bit different in each class, so I'm going to do through the ones I did in class. One was x minus 1 squared, and I said, what's the antiderivative? Another one was something like 7 over square root of 4 minus 4x squared. And another one was x minus 2 times x plus 3, or something like that. So the antiderivative of this, since this is not a product in here, we can just do the power rule. This would be, add 1 to that would be 3, so we divide by 3, x minus 1 to the third plus c. That works, and you can check it. Take 3 down, times that makes 1. This to 1 less power, which would be 2, so that matches. Derivative of c is gone. But you also have to do times the derivative of the inside. But the derivative of the inside is 1. Chain rule says do the derivative inside. And since this is 1, that works. Now if it was 2x minus 1, there'd be a problem. We'd have to fix that. Now another way to approach this one is to multiply this out. Go x minus 1 times x minus 1, which is x squared minus 2x plus 1, and then take the antiderivative of that. The antiderivative of x squared is 1/3 x to the third. Antiderivative of minus 2x is minus x squared. And the antiderivative of 1 is plus x plus c. Now, if you multiply this out, it won't look exactly like this. It'll vary from this by a constant. Well, these two constants don't have to be the same number. So either one of those is a okay antiderivative of that. Let's go to this one next. So just like this is a product, so we can't do the antiderivative of just each piece, but we can multiply this together and call it x squared minus 2x plus 3x is plus x minus 6. Antiderivative of this would be 1/3 x to the third plus 1/2 x squared minus 6x plus c, and that would be the antiderivative of something like that. This one, a lot of people look at that and say, I don't have any clue how to do it. But if I tell you that I can factor a 4 out of this, it's under the square root, so it would be 7 over square root of 4 times the square root of 1 minus x squared. That's how I would factor a 4 out of a square root. It stays in a square root, but it's just a separate one. And then the square root of 4 is 2, so I have, and if I pull this over, I got 7 over 2 times, and I think I made this minus in the class. So I'd have minus, and then this would be 1 over the square root of 1 minus x squared. And you should recognize that with either arcsine or arccosine derivative. So the antiderivative of this would be either 7 halves arc sine, or sine inverse, of x, but it has a negative, so I'd have to put a negative, and plus c. Or, if I use the negative on this, that would be arc cosine x plus c times 7 halves. So either one of those would work for the antiderivative of that. And we'll get more practice on these tomorrow.